Okay, well, welcome back, everyone. It's been great to email with you all and kind of see the articles that you're working on and get a sense of your topics. So that's been really great. And I appreciate kind of that, the back and forth, like emailing, kind of figuring out if the article fits, if it doesn't fit. If you have your article for the article critique assignment, and you've had it, don't worry about it. But it's just nice to chat with you all via email. And I want you to feel, if you have questions, you can reach out to me because that's what I'm here for. So this week we're going to talk about kind of descriptive statistics. And I want you to think back to your articles. There's generally a table where people talk about the percentage that are men and women. They look at different racial and ethnic groups. They look at percentage of people with diseases or comorbidities, and all of that table, that summary table, that is basically what frequency distributions are. So although we use a very fancy name for it, all it is just statistics that really describe one variable. So we'll walk through it. So again, descriptive statistics. These are the types of things that if you read about them, you know they're descriptive. The other type of statistics are called inferential. So descriptive statistics just describe what variables look like, what the study or the population look like, but there's no testing, and that's the big difference. So we tend to show frequency distributions, bar charts. We do measures of central tendency, which are like the mean, the median, the mode. We do variation, which could be like a standard deviation or a range. And descriptive statistics can be for one or two variables. So univariate is one variable and bivariate is two. And it's really just a way for people to understand that maybe your sample is 90% female and only 10% of your sample has COPD or 5% has diabetes. So it's a way of understanding what's the age of your sample. Is your average age 45, or is the average age 60, or is the average age 20? So descriptive statistics just give the reader a picture of what your sample looks like. Again, not testing, just describing. And this is what we're going to talk about. So we'll talk about the bottom two bullets, the measures of central tendency and variability. We'll talk about those in 8B, but right now we're just going to talk about ways to visually show data, right? Data for one variable or two variables. So we're going to show distribution, some graphs, and we're going to talk about skew. A lot of people talk about it in the culture. Oh, that distribution is skewed. But what does it really mean and why do we care about it? Those are two really key pieces of information. So I pulled this frequency distribution from my own work, and I want to show you a couple of things. That this is an ungrouped frequency distribution of number of siblings for people who are 65 and older and rural, right? So how many siblings do you have if you're 65 and over and living in a rural area? It's ungrouped because every single number has its own place, right? There's not a range. We're not saying 0 to 2 or 3 to 5. Each number of siblings in a family is reported here. So you can see this is the number of children in a family, right? So, or number, this probably should be siblings. So really only one person has no siblings in this group. And you can see that the majority of people seem to have either one sibling or two siblings. And then there's some over here that have 4, which many people say is surprising because it's this idea that in rural areas, people have larger families, but that may not be the case. So we're looking at the number of children, right? This should be siblings, I'm sorry, number of siblings. Then it's the frequency, how many people have 1 sibling, 2 siblings, 3 siblings, 4 siblings. And then what percent is that out of the total? The valid percent in this case is the same as the percent. It just means that if somebody didn't answer and said, I don't want to tell you how many siblings I have, we would take them out of the count for the valid percent. So don't worry right now about that here. And then the cumulative percent tells you what percentage of people have between 0 and 3 siblings, and you could say, well, 54%, right? So this brings in everybody before it, right? What percentage of people have 0 or 1 sibling? 29%. What percentage of people have, I gotta go across from 4, right? Between 0 and 4 siblings, 66.7%, right? So just a way of looking at it. Number of siblings, please ignore this, siblings, right? How many people fall in this group, and then what's the percent? And I'll show you in a second. I'll give you another example. This is a quiz. Let's say that if you're not wanting to go with the rural siblings, that you're looking at a quiz and you see that these are the possible distributions of scores in a quiz. And you see how many students in the class. Apparently there were 53 students, right? And this is how they distributed amongst the scores, right? And you can see that, let's say the 5 is the A, 19% of these students scored in the highest category and received the highest grade. So it's just a way of looking at a distribution of scores, distribution of siblings, right? And you see that. Now, and I'll show you the difference in the next slide, but before we said how many people have 0, 1 sibling, 2 sibling, 3 sibling, 4 sibling, right? All the siblings. Here it's condensed. So it may not matter to me if you have 1 or 2 siblings. I would like to put them together in a group, you know, because I think theoretically having no siblings might be different than having 1 or 2. And then maybe according to my theory, 3 to 5 siblings is an important range. And then those having 6 or more siblings, that might be another important category. So the data we had before for individual people is then, it's consolidated. So we can see here that about only 4.2% of the people said they have no sibling, they're an only child, a singleton, right? And then if we look at 1 or 2, 45%. 0.8 had 1 or 2. If we look in the upper ranges, right, 3 to 5 siblings, only 25% had 3 to 5, and only 25% had 6 or more. So it looks like, if we think about it, the large group in categories is this group here, right? And then cumulative just count. So if we said, you know, what percentage of the sample had either no siblings or 1 or 2 siblings, we'd say half, right? So this sample, in terms of number of siblings, is quite low for what we might expect for a rural sample. And I wanted to show you this combination. You see here, right? 0 remains none. 1 and 2 are collapsed. So 1 and 2 siblings, there are 11 people that have 1 or 2 siblings, they're collapsed here. 3 to 5, right? These people who are 6 people, they're collapsed here. 6 or more, it's all this group. So it's 3 and 6, right? 6 people here, they're collapsed. So we're just taking this more widely distributed individual kind of level of number of siblings, and then we're collapsing it into categories or ranges of siblings. And another example here, in case you prefer an example that deals with more like student or things we encounter in our classes, look at the test scores. I want you to really be careful here because there's something going on that's problematic, right? In this class, we have 40 students, and these are the class scores. 70 to 80 points, 60 to 70, 50 to 60, 40 to 50, 30 to 40, 20 to 30, right? And I'll tell you what the error is. These categories are not mutually exclusive, right? So, for example, if I score a 30, are you going to count me here, or are you going to count me here? If I score a 40, am I counted here or here? Whenever you regroup data, you want to make sure that a person can only be placed in one category. And here, the person can be placed in 2. This would be better saying 20 to 29, 30, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, right? We don't want to have these non-mutually exclusive categories because we don't know if I put someone here, did they score between 20 and 30? They could also go here if they're 30, did they score between 30 and 40? So we want to make sure that these are not the same number. And this is another way of demonstrating, and for many of us, I mean, I'm a visual learner as well, so for many of us, we want to see what the data look like, right? And how the scores kind of played out. And this that you see here on the histogram, this is a frequency distribution that has skew. So think about how this looks when we go to later slides. But this is the number of students that scored 0 to 20, 20 to 40, right? 40 to 60, above 60 to 80, and then 80 to 100. So you can see that each of these bars, we can visually see how people did. A lot of people scored right in the C to B, and a few in the A, and then the tail was in people who did in the lower level of scores, right? So we can see this visually by not looking at numbers, just looking at where this tallest bar is, and that's where you know, the majority of students scored on this exam. So histograms are just a quick way to look at visual data and see scores. And another way is a frequency polygon. And it plots all of the different scores of the students. And you can see here that the peak, or the highest number of students, scored 85, right? So it looks like if we count up, about over 140 students got an 85, while if we look at 45, one got a 45, and look at 145, maybe one or two. So we can see where those scores kind of all hang out or cluster. So again, here, we see here, the scores are clustered in this area. Here, we see the scores are clustered in this area. And if you overlay them, if you overlay a bar chart or a histogram and a frequency polygon, they should have the same look for the same data. So if we've constructed these right, we want to make sure that both of the visual displays look the same, and they do. You can see that here, these are where the peaks are in the data, and these are where the valleys are. So we've heard this a lot, and the normal curve goes back to many of the early statisticians who created it for distributions of things like IQ and other things. And unfortunately, there's a bit of eugenics history of a lot of the ways that we look at distributions, right? But that aside, we're going to understand what is a normal distribution and what is skew, because people talk about skew all the time. So this is a theoretical distribution. The normal distribution does not really exist. That in real life, data can look that way. Scores on an exam can look that way, but it's really something like, it's kind of like a unicorn of statistical distributions, right? That we know what it looks like, but we rarely accomplish this in real life. So real distributions don't often look like this. The characteristics of this distribution to be normal is it's symmetrical. You see, if you folded it in half, it would fold on its side. It's unimodal, meaning there's one large mode, one large peak. It's bell-shaped, right? We think of the bell shape. And that the cluster of scores, right? This is the cluster of scores. They remain in the middle of the distribution, and that there are few scores at the lower extreme or the higher extreme. So this is the theoretical unicorn, non-real, but theoretical distribution that we call the normal distribution. This is kind of the reality of what we see. I'm going to explain to you and give you examples of skew, but can you see the difference? This is the normal curve, bell-shaped, symmetrical. We could fold it in half, it would look equal. If we look at this curve or this curve, These are mirror images, but you cannot fold them. They're not symmetrical. So we describe distributions when we say they're skewed, it's in relation to how they differ from that theoretical normal curve. And I want you to see the difference, that when we call it right skewed or positive skewed, the tail is longer. So this tail here is longer to the right. So that's the positive skew or the right skew distribution. Conversely, right now, just get a sense of the shapes, that this is the left skew or the negative skew, right? That the numbers in this distribution would be skewed to the negative, and it is skewed to the left. The tail appears to the left. Now I'm going to give you examples, right? This is the normal distribution, symmetric, right? Theoretical, symmetric, bell-shaped, unimodal, right? One mode. This is the right skewed or the positive skewed. This is the left skewed or the negative skewed, right? Now I'm going to give you some examples or some ways to really think about what skew means. So here, if you're positively skewed, you have a lot of low values, right? So a lot of values are here in the more negative part of your, or lower part of your number range, and few higher ones. Positive skewed, lots of low values clustered here, very few high values. Negatively skewed, it's the reverse, lots of high values, very few low values. This is the higher end of the, when we graph something numerically. So I'm going to give you an example. Let's look at income. Income in most countries has a positive skew because very few people have a high income. So most of us with income might fall in the lower levels of income. It's only a few people who are really pulling that value up. And then for negatively skewed, if you think about it, it could be, like let's say BMI, or it could be a clinical test value where most people have high values of the test, but only a few outliers have a low value. So most people in your sample have a high BMI or a higher body weight, and there are a few people in the sample who have a low body weight. Or there are many people who have high blood sugar in your sample, let's say, and a few have low blood sugar. That would be negatively skewed. Positively skewed, right? Think of income. Positively skewed, think of height. You have somebody who is 6'7". Very few people are in the higher end of height here. Negative, think of many people having high BMI or many people having high blood sugar, but people with low BMI or low blood sugar falling in this end of the distribution. So just an introduction to skew, just an introduction to kind of frequency distributions, looking at how we describe a particular variable. In the next set of slides, what I'm going to do at the end is I'm going to show you a demographic table, and we'll go through it and talk about level of measurement, what kind of test, we'll bring in some more examples, and I'll show you more. But just think about the differences for a group distribution, closing categories together, or a frequency distribution that lists everyone. And then think about this theoretical normal curve, and think about if you have a lot of people on one end of the curve, or one end of an exam, or one end of a test, or one end of a measurement, and a few that are outliers, where they fall is where the skew exists. So just an introduction. I'll recap in the next video. Thank you all for being here, and I'll talk to you soon.